In this video, we extend our ideas of aqueous solutions to look at electrolyte solutions and non-electrolyte solutions. It turns out that many aqueous solutions can conduct electricity, and solutes that produce electrically conductive solutions when dissolved in water are called electrolytes. It can be shown that the electrical conductivity of these solutions is actually due to the presence of dissolved ions, positively charged cations and negatively charged anions, which become highly mobile in the presence of an electric field. We can use the dissolution of table salt, sodium chloride, to demonstrate the principle. We can represent this process via this chemical equation here, showing solid sodium chloride being dissolved in water to produce an aqueous solution, as designated by the AQ subscript. This equation, however, is probably better represented like this, where we see that the dissolved sodium chloride salt is represented as separate ions, the positively charged Na plus ion, the sodium cations, and the negatively charged Cl minus ion, the chloride anions. So it seems that water as a solvent is able to do something quite unusual to the solid sodium chloride crystal. It is able to break apart the structure of positive and negative ions within the ionic compounds, resulting in free ions dispersed throughout the solution. We can represent this pictorially as well. Here we have a two-dimensional representation of the crystal lattice of sodium chloride with alternating positively charged sodium cations and negatively charged chloride anions. When we add water to this crystalline structure, the positively charged cations and negatively charged anions become physically separated as solvated ions, meaning they end up being surrounded by water molecules, which keep them as stable dissolved particles in the solution. If we were now to take this solution and stick a pair of electrodes in it and hook those electrodes up to a voltage source such as a battery, we would actually create a closed electrical circuit. In the external circuit, the electrical current is maintained by the movement of electrons in the copper wire. So in the external circuit, the charge carriers for electrical current are electrons. In solution, however, the charge carriers are positively charged cations and negatively charged anions. And what we see is that the positively charged cations, the sodium ions, migrate towards the negatively charged cathode in the presence of an electric field. And the negatively charged anions, the chloride ions, migrate towards the positively charged anode. This phenomenon, as we know, occurs due to the attraction of opposite charges. So it turns out that any soluble ionic compound will dissolve in water to form freely mobile ions, cations and anions, and therefore any soluble ionic compounds are classified as electrolytes. It follows, therefore, that any insoluble ionic compounds that do not dissolve in water, are not going to produce the freely mobile ions and are therefore classified as non-electrolytes. You may therefore think that any substance that dissolves in water will produce an electrically conducting solution, but that's not the case. Not all soluble compounds are electrolytes, and in fact we have many molecular compounds, for example sucrose or sugar, that can dissolve in water but do not produce ions. We can represent this process as solid sucrose, C12H22O11, in its familiar solid crystalline form, being transformed into dissolved sucrose or dissolved sugar as represented by the AQ subscript. And it does this without breaking apart into ions. In fact, there are no individual ions in the molecular sucrose structure. Now, a substance such as sucrose would be considered a non-electrolyte, being a substance that, even though it dissolves in water, it produces a non-conducting or poorly conducting solution. Again, due to the fact that no mobile ions are formed. The fact that sucrose, a molecular compound, is a non-electrolyte may lead you to think that all molecular compounds are going to be non-electrolytes because they don't contain ions. But that's not true either. Not all electrolytes are ionic in nature. There are, in fact, molecular electrolytes, with the most important class being the acids, for example, HCl or hydrochloric acid, HNO3, nitric acid, H2SO4, sulfuric acid, and HC2H3O2, acetic acid. As an example, the molecular compound hydrogen chloride is a gas at room temperature and pressure, but when it is bubbled through water, the HCl molecules dissolve as represented by the AQ subscript, and it is only then that we refer to HCl as hydrochloric acid. When HCl is in its gaseous form, it is known as the molecular compound hydrogen chloride, but once HCl is dissolved in water, we refer to it as hydrochloric acid. Now, one of the defining features of an acid is a substance that dissolves in a solvent to produce H+ ions, and it turns out that hydrochloric acid is actually better represented in solution as separate H+ ions and separate Cl- ions, dissolved and dispersed through the aqueous solution. And so we have this slightly counterintuitive notion that a molecular compound, hydrogen chloride, which contains no ions, is actually split into two ions by water, and those ions are able to sustain an electrical current in the solution in the presence of an electric field. And so what we have is an example of an electrolyte that is a molecular electrolyte. And these acids here are some of the most common and important examples of molecular electrolytes. We can further classify electrolytes into strong electrolytes or weak electrolytes. Strong electrolytes are substances that exist almost exclusively as ions in solution. In other words, the substances dissociate completely to form ions in solutions when dissolved in water. And we have already seen a couple of examples of strong electrolytes, including ionic compounds that are soluble in water, such as sodium chloride, which dissociates completely into Na+ ions and Cl- ions in solution. Other important examples include the 7 strong acids listed here, including HCl, which is best represented as separate H+ ions and separate Cl- ions when dissolved in water. These examples are quite different to weak electrolytes, which are substances that ionize only slightly upon being dissolved in water. And examples here include weak acids, such as acetic acid, and weak bases, such as ammonia. Here is an equation representing the ionization of acetic acid, whose formal name is ethanoic acid. Acetic acid, despite being a molecular compound, dissociates in water to produce the H+ ion and the acetate ion in a 1-to-1 ratio. The unusual feature of this particular chemical equation is the presence of these double arrows, an arrow going to the right as well as an arrow going to the left, which actually means that the chemical processes described here are significant in both directions. In other words, the acetic acid molecule is dissociating to form the hydrogen ion and the acetate ion, while at the same time the acetate ions and the hydrogen ions are recombining to form the acetic acid molecule. And so we have a process here that's appreciable in both directions. The reason it is an example of a weak electrolyte is that at any point in time, only a small percentage of the acetic acid molecule exists in its dissociated ionic forms. We will deal with weak electrolytes such as weak acids and weak bases in much more detail later in this video series. In a follow-up video, we look at how to determine what substances are soluble in water and which are insoluble by looking at a series of solubility rules.